This is the project demonstration video for the VanWyn High-Power Wireless Power Transfer team. This video will showcase the setup used to conduct tests to determine the functionality of our project and showcase a diorama constructed to show a real-world application of our project. For the test setup, to prevent signal leakage, we reinforced a 1 meter by 1 meter Faraday cage constructed by a previous senior design team by adding an additional layer of wire mesh on all sides of the cage. We also added the same wire mesh on the floor of the testing area. We affixed a wooden stand holding the transmitting antenna on the floor. We attached the receiving antenna onto the far end of the Faraday cage. This allows us to change the distance between the two antennas without having to remove any components from within the Faraday cage.
For the components on the transmitting side, we used the Mini Circus ISC as our signal generator. It is powered and controlled via USB by a laptop. The signal generator sends the signal to a Mini Circuit CHL power amplifier. The power amplifier is mounted on a heatsink and fan that keeps it cool throughout operation. The cooling fan is powered by a DC power supply module at 12 volts and 2 amperes. The power amplifier output is fed to the Furious FPV 2.4 GHz transmitting patch antenna on the wooden stand. On the receiving side, we have the same Furious FPV patch antenna. The antenna is connected to a Mini Circuit fixed attenuator. This attenuator reduces the output power and ensures that our Mini Circuit's smart power sensor is not damaged.
These are the 4 general procedures for our conducted test. We changed the distance between the transmitting and receiving antennas by moving the entire Faraday cage. We can observe the distance by looking at the tape measure secured on the floor. During testing, we changed the transmitted power using the PUTI virtual terminal software. Using this software, we can set the frequency and power output of our transmitting antenna. We measure the received power using the Mini Circuit PWR Smart Power Sensor with the Mini Circuit Smart RF Power Meter software. The software allows us to input the desired frequency, observe the temperature of the power sensor, and measure the power received in dBm or watt.
For each test, we make sure to record the power transmitted, the distance, and the power received. The data is tabulated and plotted to observe the relationship between the distance, power transmitted, and power received. During our testing, we managed to transmit up to 0.23 watts of power with 1.15% efficiency across 1 meter. However, more power was received at shorter distances. The results are summarized in this graph.
For the diorama, we assembled a model Capitol building with an LED lighting kit to act as our load. We constructed a smaller 30 cm tall Faraday cage to fit into the diorama. The top to bottom construction of the Faraday cage is to portray the wireless transmission of solar power harvested in space to the receiving ground station on Earth. To rectify the power received at the receiving antenna into DC voltage and current, we use the RFD102A TB rectifying circuit. The output of the rectifying circuit is then connected directly to the positive and negative terminals of the LED lighting kit. We place the same components used in our test setup in this glass cabinet. This allows us to showcase all the components used in our project. In conclusion, we have constructed a system capable of sending power wirelessly via electromagnetic wave at 2.5 GHz frequency. This system is able to deliver 0.23 watt of power over 1 meter with 1.15% efficiency. The wireless power received can be rectified into DC voltage and current to light up a diorama.